So thank you everybody for joining us today. EngineSoft is a key partner in design process innovation. Today's agenda is I'm going to do a quick introduction. My name is Hannah Arnold. I also have Chris Garcia. He is going to go over flow analysis with you after the introduction. And then we are going to pass it over to Dr. Andreas Vlahinos, who is going to go through Creo simulation live with everyone. We'll hold questions at the end, but throughout, the presentation, feel free to ask any questions in the chat box. All right. So a little bit of background on us. EngineSoft USA is a multinational company. We were founded in 1983 by a group of engineers passionate in powerful advanced CAE technologies. Today we are formed of over 300 experts in new technology and leaders in virtual prototyping. EngineSoft provides customized solutions, leading innovative technology, and complex simulations. So there are 7 locations throughout the world. The home office is in Trino, Italy, and then we also have a location in Turkey, Germany, Sweden, England, and France. We also have our location here in Dallas, Texas, and some of you may have received the EngineSoft newsletter recently, but we merged with MotionPort. They are a powerful company in multi-body dynamics as well as a few other competencies. So we are excited to grow with them and move forward from here on out. So here's some of our customers by different verticals. You may recognize some of these people in automotive, aerospace and defense, energy and construction, industrial, appliances, retail, and consumer, as well as metallurgy. Some of our distinguishing characteristics are we've performed over 4,000 consulting jobs with different entities. We have over 1,500 customers, companies using the software that we essentially distribute. We offer over 130 training programs yearly, and we've engaged in over 60 technological transfer projects and research with universities, academia, government, things like that. Some of our skills are fluid dynamics, fatigue and durability, crash test and fast dynamics, process simulation, high performance computing, mechanics, tolerance analysis, environmental and vibroacoustics, optimization, and multi-body. So with that, I'm going to turn everything over to Chris Garcia at this point. So he'll be able to go through flow analysis, and we'll go on from there.
Thank you, Hannah. Let me go ahead and share my screen. And let me know if you can see my screen.
I can see your screen.
All right, perfect. So as Hannah mentioned, my name is Chris Garcia. Give a quick introduction about myself. I graduated from Texas Tech University in 2014 with a Bachelor of Science in Mechanical Engineering degree. I worked in the power industry for about 5 years prior to joining EngineSoft USA. And today I am one of the CFD application engineers here at EngineSoft USA. So today we're going to go over Creo flow analysis extension. I'm going to give you the high-end view of Creo flow analysis and then jump into a quick demo. So what is Creo flow analysis extension? Creo flow analysis is a CFD solution that allows engineers, designers, and analysts to simulate flow fluid issues directly within Creo. Creo flow analysis is embedded in Creo parametric, and you can do the model definition, pre-processing analysis, and obtain results, without leaving Creo parametric. Why do we need this? Engineers lack the tools and skills to perform CFD analysis. Oftentimes, CFD requires third-party analysis tools and high-priced analysts. It's also very time-consuming to complete, especially in early-stage design. Without CFD, there's an over-reliance on physical prototypes. Creo flow analysis supports concurrent CAD and CFD analysis using a common data model and for CAD, and CFD. The seamless integration of technology eliminates traditional barriers that prevent designers and engineers from using analyst tools during design and development. So basically, Creo flow analysis is easy to use. It's embedded within parametric, easy model creation, rapid simulation turnaround time, and high accurate results. If you're a Creo user at the moment, you'll find that it's a familiar Creo command ribbon in the UI, context-sensitive menus, RMBD command access, simplified workflows, and again, since everything is embedded, you just have a single GUI for setup, simulation, and post-processing. As I mentioned earlier, it's embedded in Creo Parametric. So there's a seamless integration of CAD and CFD. 3D CAD is directly used for flow analysis, so there's no need for translation or any need to copy geometry. There's no need to clean up any CAD data prior to mesh, which I know in some previous experiences, I know that the CAD cleanup can take some time. And with this tool, you can get straight to working and not have to worry about any cleanup. All data is associatively linked to the CAD model, so any kind of analysis update automatically update when designs are modified. I know this can be particularly handy, especially if you're working on a design and you want to change something, let's say on the fly. This is a handy tool to come into play. So with Creo flow analysis, there's an easy model creation and analysis setup. There are configurable templates that rapidly create and reuse templates to speed up analysis setup. There's an automatic and efficient meshing, works 100% of the time. High quality, high efficiency mesh that roughly half the cells compared to competitive solution. Superior quality that includes shape and aspect ratio, and one-step creation of separate fluid and solid domains. Nice thing about Creo flow analysis is the rapid simulation turnaround time. So in my previous experience, I know that pre-processing and building mesh takes up quite a bit of time in the CFD world. With Creo flow analysis, we pretty much cut that down very, very small. So Creo flow analysis uses a proprietary algorithm, speeds runtime and convergence. It runs half the iterations of competitors, including ANSYS Fluent, Star CCM. The mesher is completely integrated with the solver. Its built-in processor works the minute you start the solver, and there's no waiting for a mesher or solver convergence. With Creo flow analysis, you'll get highly accurate results. This is because Creo flow analysis uses comprehensive physics, high quality and fidelity of mesh for increased accuracy, high stability for complex geometry and extreme conditions. So what Creo flow delivers as far as business value, you can streamline your product development and speeds time to market. And you can do this by concurrent design and CFD. You can reduce product development costs such as prototyping, rework, scrap. You can start by identifying and resolve design flaws early in the process. You can increase the market share and competitive differentiation. This is by increased product quality and performance. You can reduce aftermarket service, warranty, and repair costs. And then you can demonstrate compliance and due diligence with Creo flow analysis. So this slide is just kind of a basic overview of the 3 different packages that are offered for Creo flow analysis. You've got the Creo flow analysis basic, Creo flow analysis plus, and Creo flow analysis premium. Okay, so I'm going to go ahead and move on to our quick demonstration. Before I do so, are there any questions up to this point?
Does not look like anybody's asked anything so far, so we're good.
Okay, perfect. So let's just go ahead and jump into it, and I'll show you how easy it is to use Creo flow analysis. I like to use the example of, let's say I'm an engineer who's working as a nozzle designer for water nozzles. right away, I'm in Creo parametrics and I've got my model already set up. So let's go ahead and activate Creo flow analysis. This might take a minute to do. But just like this, we haven't left Creo parametric, and now we can start the actual setup. You can do this by going to Creo flow analysis, a built-in flow analysis wizard, which will take you each step by step for the setup. And for my first step, I'm going to go ahead and select some basic packages, which includes the flow, turbulence, and streamline. These are going to be the bread and butter for all of your CFD analysis. For this case, I'm just going to ignore gravity for a second. In the next page, I'm going to set up the fluid domain. And for this particular problem, since I'm really interested in the nozzle and the flow coming out of this, this nozzle, I'm going to select the internal. And my computer likes to freak out, but we're all good. The nice part about Creo flow analysis is that the openings are automatically detected. In the case that your holes aren't detected, you can go to openings, go to faces, and manually select each face. For convenience, I'm just going to go ahead and move forward. And just like that, our fluid domain has already been created. Yes, it's good. Keep moving forward. So now I'm going to add my water to this analysis, and I can do this one of two ways. I can either select the fluid domain that was generated, or I can go to the model tree and select the fluid domain. Your fluid domain is usually your model demo, and in this case, it's model demo fluid. So for ease, I'm just going to go ahead and select fluid domain. Going to change the properties from air, material from air to water. Going to leave this as a constant density. If you were to want to change your density, or if you wanted to change your material, that can easily be done in the wizard. And now I'm going to go ahead and select my inlet and outlet boundaries. As everyone knows, with CFD analysis, you can't have a CFD analysis without inlet and outlet conditions. So let's start with the inlet. And just so I can make sure we have the correct inlet, so let me just select one. There we go. And just for convenience sakes, I'm going to go ahead and rename this to inlet, just as a good practice, so that I know which one is which. Select my inlet. And let's say for my project, my manager or my boss has specified that the inlet to this nozzle is 50 psi, or roughly 350,000 pascals. So we know what we're working with. I'm going to go ahead and release my streamlines. That way I can see the flow that's coming out. And for my outlet conditions, let's just say that this is going to be open to atmospheric pressure. So we're going to go ahead and change this from velocity to pressure. And we'll change this to atmospheric pressure. No need to release the streamlines of the outlet. For this case, there are no other surfaces that we need to apply a boundary condition or any volume parameters. In the simulation tab, you can determine whether you want to do a steady state or a transient solution. For this case, we're going to do a steady state, and we're going to leave the number of iterations and saving frequencies as default. This is a pretty quick simulation, so no need to change those. And here's where the bread and butter comes from in the automatic mesher. The Creo flow analysis will automatically generate the mesh without you having to lift a finger. For this particular case, we're going to leave the default conditions alone. We'll generate the mesh. And just like that, the mesh has already been generated. At the output type, if you want to specify which variables you want to look up in your XY plots, you can do this. So I'm going to go ahead and select boundaries. And let's say I want to figure out what's coming out of the inlet. Right now we've got mass flow rate, and I'm going to go ahead and turn on volumetric flow rate as well. This will help me design my nozzle later. For convenience sake, I like to create two different plots. That way I don't have too much information going on. And just like this, we can start the simulation. So in no time, you're up and running. The best part about this is it doesn't require anybody to have a PhD. I know most CFD tools, you've got to be pretty high up there, and you've got to be a pretty good expert at some of this stuff. The nice part about Creo flow analysis is that it's not required. You can get up and going, and just like this, you've got a full-blown CFD analysis. So now that the simulation is done, we can do some post-processing tools. Let's say I wanted to look at the section view of the downstream of this model. I'm going to change this to velocity just because most engineers have velocity in their mind. And just like that, we can see the velocity contour from the inlet to the outlet. Okay. And likewise, you can do an iso surface plot that'll show everything in the 3D view. We can do anything above, let's say, for sure. Let's say anything above 200,000. And we can see all the spots in 3D space where the pressure is above 300,000, or excuse me, 200,000. Likewise, there's streamlines where we can actually see the streamlines coming outside of the inlet. And let's get a little color in here, that way we can see what's happening. And now we can see the velocities of velocity streamlines coming out of this model. If we wanted to, we can even animate this. Just like that, we can see what's happening inside of our nozzle. So I'll take a quick break and see if there are any questions up to this point.
We do actually. We got a question from a Mad Tripathi at Coney Elevator. Hopefully I was able to pronounce that correctly. Forgive me, Ahmad, if I pronounce your last name wrong. His question was, when creating a mesh refinement zone, what is the best practice for deciding how small to begin cell refinement iterations?
Yes, good question. We did this with Otis elevators, and by default, the cell size specifications for refinement zone is an absolute. So basically, the knowledge about the sizes of your geometry can be used to determine what value to try first. Basically, for an example, if you have a relatively small channel, let's just say it's 0.3 millimeters in your model, you would want to make sure that the flow paths have at least 3 cells in the width. So you could try a cell size of, let's say, 0.1 millimeter, and then go from there.
Perfect, perfect. Now, also, we had one other come in from Jawahar while you were explaining that one. He said, is it possible to specify a cell size on a particular surface?
At the moment, it is not possible. Creo Flow only supports a global cell specification size.
Wonderful, thank you.
And so, going back to my example, now that we have a flow, we can say, all right, now I can look up my flow coming out, my mass flow. We know my area. Now we can figure out the velocity of this nozzle and change as needed. And any iterations can be done very quickly in Creo flow analysis, and we're good to go. And I'll leave it for any other questions up to this point.
I don't have any coming in currently.
Okay, perfect. Well, just like that, it's easy to create a project from beginning to finish. And just like that, we have CFD results. So that's all I have for now. I can now turn it over to Andreas, and he can start discussing Creo Simulation Live.
Good morning. My name is Andreas Vlahinos, and I'm just a knowledge worker. The first half of my career, I spent it as a university professor, teaching computer-aided engineering courses at the University of Colorado. And the last half, the last 15 years, focusing on solving new, unique, and difficult industry problems by adapting the latest technologies like what you will see today. So I'll tell you a little story first. Once upon a time, we had many steps and many tools. We had the concept. This is a transmission gear from the Black Hawk helicopter. And we had the CAD model. And then we take it to another program to do the featuring. Like, let's say, take the fillets out of this region. And then we take it to the meshing program. And we mesh it, apply loads and boundary conditions. And then we go to a solver and solve it. And then we go to post-processing to look at it. And then we evaluate the results. We talk to manufacturing for feedback. We do design modifications. We go back to CAD and continue. Now, to give credit, there is a lot of progress in capabilities in CAD, parametric and direct, like flexible modeling. There is full associativity between CAD and CAE. There's automatic meshing. The workflow can be captured and repeated, and we can do optimization on the results, and we have multi-physics integration. And when you think it doesn't get any better, it does, because now we have Creo Simulation Live, which we can do structural, model, thermal, and fluid simulations within the CAD environment. And we can get 80% of the simulation results for 1% of the effort. So the question you need to ask yourself, if I put 1% of the effort required to set up a CFD or a structural or thermal problem, and I get 80% of the results instantaneously, will be that worth to me? Truly now, finally, we have the tools to do simulation-driven design. We utilize simulation much earlier in the design process. That's where it really counts, when you make design decisions. As in, I will show you, we can do quick answers to what-if questions very fast. The flow domains, for example, update automatically. If here's a little example, we'll do later, a heat exchanger, which you can see if we do change the number of pins or the diameter or the shape of the top, I can automatically change this thing. I don't need to worry about anymore about obtaining the fluid domain, meshing the fluid domain, imposing boundary layers and inflation layers on the domain, apply the boundary conditions, run it, wait, look at the results, and make a decision, and then start over again. This is amazing for automatic design exploration, as I will show you live, with the BMX capabilities in Creo. And if you can do these things very fast, what's the big deal? You can do your job faster? Yes, but also enables breakthrough and disruptive innovation. I would love to show you more examples. We have a one-day course on this, which I can show you examples. We have about 7 patents last year just by using these tools. Anyway, so what I will do, we have an effort to shrink the devices. They get hot. We need to cool them. How we design these cooling devices. So the demonstration examples I will show you, it's a very simple one to see how we set it up. Then we'll optimize and we'll do this automatic design exploration of a little heat exchanger. And then we'll take this cell and tube heat exchanger and try to find out the flow or the impact, let's say, of the inlet direction or the orientation of the inlet or the number of tubes instantaneously. That's the big deal, that you do real-time simulation. So if you have complex geometries like this, now in Creo we have amazing lattice structures, and this is a heat exchanger. The heat sip is here, the fan is there, and the fan blows down here. Can I find out the temperature distribution on this heat exchanger? Look, this geometry. Try to imagine for you guys, which you ever did either CFD or structures, how will you mesh something like that? Try to imagine do CFD on this. See how many inflation layers you will need. But then in Creo Simulation Live, this is the fluid domain. It comes out automatically, and this is the pressure distribution from the top, so you can see the flow hitting these areas. And of course, you can do your flow lines and you can find the velocity profiles and etc. So let me jump to to a few examples so we can see it live. Okay. So let's say we have a little tube here. That's the very simple, silly example, which we want to find out if we impose a flow here, how much would be the pressure drop for this device. And then we have only 5 minutes to give the answer. How much is the pressure drop here? So what you do, you go to Creo Simulation Live. In here, you can add simulations. You have structural, thermal, model, and fluid. Let's say fluid. If we add fluid, the first thing we need to define is the fluid domain. So we say fluid domain, it's internal volume or enclosed volume. So if you do, let's say, the car, the external, let's do internal volume in this case. And it says, give me the surfaces, they define the fluid domain. So you get these surfaces and it finds the fluid domain and say, I'm done defining the fluid domain. Now this is a volume, this is an extraction. We used to have merge cut out to find these things. Now it's trivial and it's fully associative and it's generated automatically. Now, if you go to the tree here, we have the fluid domain. We can add material for the fluid domain. Let's add air and say okay, and see on the model tree that's it's assigned. The next thing is the velocity. Let's go put the velocity. We're going to do it in, let's say, what is that, the x direction. So we're going to do directional components. We'll go in that direction and let's say put 5. Let's make it meters per second. And we select that inlet and say okay. So now, so it's simple. First, we specify the fluid domain, the inlet, and now let's put the pressure outlet here, and we're done, believe it or not. That's it. Now you can say, can you please solve it? You know, and it does the magic, and immediately we start seeing the results. This is there is the big deal, my friends, is there is a blend between CAD, defeaturing, meshing, pre-processing, solver, and post-processing. There is no these phases are not here anymore. You can see live, real time, the results, you know, and you can say, okay, let me forget the velocities, let me see the particles, you know, so you can say, oh, gee, I have these two zones here. Maybe I could do much better to avoid the recirculation by redesigning that component, okay? Or you can say, can I see I don't want to see the particles, I want to see the flow lines so I can identify right away the recirculation regions. This is pretty damn amazing. So here I can change the shape like that, and I can shape the scenes like that and make it much better flow or whatever else you want to do, and say, oh, but don't forget what I asked you. I asked you to find me the pressure drop. Okay, I can go to so everything is here. You don't need to go to any menus or pull out. I want to see the pressure profile. Okay, so you can see it's a higher pressure there and say, but I ask you for the pressure drop. Okay, I'll put the simulation probe. I will select the maximum on this phase and the pressure is, 55, you know, pascals. So real-time simulation results all within the model, and I can close this. So this is how easy it is to set it up, okay? So are there any quick questions on this? Nice. So if you don't have questions, is that you don't pay attention or it was really clear. Anyway, let's go to another simple example. Let's go to an example with a little heat exchanger. Here,
Actually, Andres,
yes,
we did have one question come in from Alessandro.
tell him it's
Based
too
on
late.
your
No, I'm just kidding. I'm just kidding. Okay, go ahead.
based on your experience, what is the amount of agreement between the CFD results in Creo Simulation Live and Creo Flow Analysis?
I hate that guy. This this is This is tricky. Okay, let's answer. Let's explain that a little bit. But that takes a little bit time of my presentation because I had only 19 minutes. So,
That'll work. I mean, I'm sure you can address that at the end if
yeah,
it'll work out better.
let me address this. Is a very serious question. The question really, if I rephrase it, can I use Creo simulation live results for a very critical component which, it's mission critical and it will break? The answer is no. The Creo simulation live will give you design directions, how you design the part. When you're done and you have optimized it, as I will show you in this little example, yes, then you can go to, the flow analysis or to Fluent or to CFX or to Star CD or whatever and validate your results. This is not a tool which will give you 100% accuracy for 1% of the effort. It will give you 80% accuracy, but for 1% of the effort, and it will give you real time so you can do design decisions. Okay, so let's say here we have a heat exchanger. There is a heat load on the bottom. Yeah, I forget, I mean, it was 5 watts or something. And we have a pin fin similar to what I showed you earlier. And I have a probe here that what happened in the live simulation, you can see the results, let's say in this case, the temperature, and you can capture the maximum temperature on the chip, and it says it's 160. Darn, the electronics need 120. What can we do? Is anything we can do? Yeah, let's try to change maybe, and you can see that the hot is in the middle, and out there it's not as hot. So what we want to do, change maybe the profile of the fins, and let's say if having 0, let's make it 50 millimeters. So now this is you know, the, the modification. So I just say regenerate. This is the power, my friend. Here, I just regenerate, I modify a design variable, I regenerate it, and it gave me the results. And it says it's 136. Darn, that won't quite do it. Is anything I can do? Let me undo this, okay? So you undo it, it solves it on the fly. Yeah, it's not, I say it live, it's quite a lie. It takes about 50 milliseconds, or it takes about a second, let's say. Okay, depends on the size of the problem. So, but a second I can put up. By the time I said it takes longer to regenerate than solve. This is pretty damn amazing. Okay, you can say, man, is anything I can do? Can maybe I change the pin diameter to, let's say change the pin diameter. What is it? This is 10. Let's make it what? Let's make it 12, because then I get more surface area and I say regenerate. Boom. And I get the results. Now it's 160. This didn't do it either. What can we do? I mean, can we maybe change the number of pins? Can I modify it? Where do I have it here? There is one, I think is this one. Yeah, number of pins. Let's make these, instead of 25, just give me a number. Let's make it 20. Boom. And I put a lot more pins. Okay. And I said generate. And there's all stagger and stuff like that. If you see them, from the top view, it's pretty amazing. So you say, oh my God, it can get, I'm getting close. Here's 123. It doesn't get any better than that, because I can modify something and instantaneously I can see the results. Okay, so I can do a lot of design exploration. So when you thought it doesn't get any better, it does, because now what you can do, you can go back to traditional Creo and say, man, I try a few guesses I have, I went in the right direction, but it didn't quite work. Can I do an automatic analysis? Can I do a sensitivity analysis? For example, if I take the height of this thing, and I go, let's say, from 0 to 50 for millimeters for the height of the dome, and the parameters to plot what I'm going to do, the maximum temperature. Okay, and I can say, okay, and I'm going to do 20 design explorations, not 10. Okay, now at this point, I ask you, you cannot blink. You cannot blink. You can blink now, but let me point out the two things you need to be watching. One is the probe. What is the temperature, the maximum temperature of the heat exchanger? And the other thing you need to watch is the shape, so you can see what's going on. So please don't blink. 1, 2, 3. So I say compute. Now what it does, the temperature is 123, and it plots me the temperature versus time. It increases the dome height, and it's 117, and it gives me a plot, and it changes the other one to 117, and it gives me the plot. So now it does 20 design iterations in about 20 seconds because it solved 20 times the same problem. Try to imagine to do this by hand. I used to be a professor, so I had my graduate students do that. And I say, go do plot that curve. And in a month, they come back and say, okay, I generated 20 geometries. I, mess them. I defeature them. I plot them. I generate the results. I found the post-processing. I did it, and I make a spreadsheet, and I get that table. And then we had the master thesis. And now we can do it freaking live in 2 minutes. Okay, and I can see right here, oh, if I want to end in my target, oh, there is hope. There is hope to do that. Okay. So let me close that, and maybe we go to change something else. Let's go change the number of pins. Okay. Um, let's do the pin diameter. Let's make it 10 so they won't run into each other. And of course, every time you regenerate, you can see the results if you go to Creo Simulation Live. But let's go back to number of pins. Okay, that's the number of pins. So we'll do another analysis and say, okay, now I'm going to play with a number of pins, so I will go, let's say, I don't know, from, what should I do? I should go from maybe 15 to 25. And I will still plot that, and I will do 2. Again, here's the time we don't blink, because now the geometry will change more. Let me clear up, and I say, go. So I do 20 design iterations. Look at it, started at 96. Oh, there is a lot of hope there, and as it goes up, the temperature goes to 120, it drops, it goes around. So you can see how you can automate the design exploration by integrating. Look at number, we keep changing the pins. You see these plateaus there? What happens, I can explain that. The spacing changes, but the number of pins didn't change. So you can have the same number of pins in its plateau, and then the spacing change such that you introduce more, numbers and more pins, and you go up. So this is pretty exciting stuff to be able to do such a fast design exploration live, without doing that. And I know you think, well, it can't get any better. I saw that. It does. It does. Okay. Here, anytime you can go to any design, you can see you have a little button here, which is not another amazing thing. You have 3 ways to see the results. You can see shaded image, you can say hidden line removal, shaded with edges, or you can toggle between results, and you can always work on this mode. Now, if you guys think it doesn't get any better, it does, because I can go back to the analysis and say, man, I solved these 3 design variables I changed, but could I do something better? Could I do, let's say, an optimization study? And I say, listen, by the way, can you please minimize my mass? Can you add a constraint that I want my temperature to be less than 120. Okay, so make sure minimize the mass and make it. And what do you want me to play with? Well, you can play with the height of the dome and make it between, let's say, 10 and 40. And you can play with the pin diameter, let's say here, and make it, I don't know, you can go between, let's say, 5 and 10, or let's say 12. And what else you want me to play with? Well, can you play with what else is a good one? Oh, the number of pins. So let's go put the number of pins, which is this one, and we'll play with this one. And all of these things, guys, is, alive. Let's say between 15 and 25. So now I did 3 individual and I saw how well it works. Now I can say, can I try these range? And I can say compute. Now don't get, you can blink here because it doesn't animate what it tries, but here it does a DOE, design of experiments. It builds the response curve, curve if you guys are doing these things manually. And then it tells you the convergence. It try to minimize the mass. And it does this, if you really look on the bottom left, you can see that the temperature updates, on the probe, which is pretty cool. I mean, come on, don't tell me you ever have seen a CAE tool. It can do that. While it's working, it can do this. Anyway, so it's, of course, the optimization is more complex and it will take a little bit more time because it try to optimize 3 design variables, regenerate the geometry, resolve the geometry. You can see down here the changes in the geometry. Okay, is there a good, this is a great time for a question if you have, so.
Yeah. So, in your experience, do most designers understand fluid dynamics well enough to use this tool?
The quick answer is no. But here is what you can do. I mean, you can educate the designer and say, listen, I want to minimize the pressure drop. I have a motor or a pump which it can handle a pressure drop of 120 psi. I want you to make sure the design is smooth enough so I can, minimize that pressure drop. Here is the a probe which gives you that pressure drop. Can you please play around with your design to do that? And you educate the design. Say, look, if you see recirculation regions, build the wall there so it won't have to recirculate. It will go and have a nice smooth flow out. So we really enhance the designers if you can explain them. And usually, if you're an engineer, these flow calculations are very difficult to do. So, this thing converts, so I can close, and it says, hey, I changed it to the design study. Do you want me to switch to that model, to the optimized model? Because I use that in the training class. Oh, by the way, there is an advertisement. Here's the training class. One day, it takes half a day to learn all this Creo simulation live, structural, thermal model, and fluid. In the rest of the half of a day, we do your problem. So you learn how to do it. So anyway, this is an engineering design tool, So if the designer doesn't know about CFD, educate them. But if it does, or you can tell him, hey, that's my goal. You can do these freaking optimizations on the fly. You can do a bunch of things, to do that. He was trying to tell me, hey, you optimize and you're already out. So let's see if I can have another one. Here is I see, let me show you to you in the section view so we can see it better. Here is a typical heat exchanger. There is flow coming in here, going around and around these tubes. here you can see the tubes. It goes around the tubes, around and around the tubes, and it comes out here. And this is, let's say, the hot, and then here is the cold coming in through here, or vice versa. And this is a typical heat exchanger. Okay, so let me go take the section out and say solve. So what it tried to do now, this is very complex because that's the fluid domain, and this is the pressure, but I can switch to, because I switched the pressure before, on the previous project problem, he thought, oh, okay, and you need pressure here, but I can switch to velocity and do these things. And if you later on a little bit, you can see that it goes out and escapes, and you say, man, I really need to put a buffer. Usually we put a buffer. So here it is. If I go there and I say, resume that buffer, what happens, it regenerates the geometry, puts the buffer there. And, I think I'm a little bit out of time. So let me go back to this and see if you guys have any questions.
That last question was from Jawahar. He's with Case New Holland. He also is asking, he says he has a complex fluid problem with multiphysics. He's asking if we have staff that can help with that.
Yeah, let me, I don't want to bust your bubble that Creo Simulation Live can do multiphysics. No, it cannot. It can do one fluid domain at a time, and it cannot do conjugate heat transfer yet. Okay, it's a tool which helps you visualize your design. And if, of course, in multiphysics, if it's the here is sort of the escalation. If you need to start for Creo Simulation Live for very simple things, okay, like this. What I show you here is, for example, the fluid on the pin fin heat exchanger I was showing you earlier, and here is the fluid on the other one. So you start with Creo Simulation Live to come close to your design. Then you can use Creo Flow extension if you have, let's say, more complex simulation, which has, let's say, conjugate heat transfer, which you have, like on the heat exchanger I show you, you have the two fluids and you have the, a bunch of other stuff involved. And the next level, if you have, let's say, moving grids and stuff, is to go to ANSYS, CFX, or Fluent. So we have the capability to do all three, So we'll be delighted to look the problem and give you a code for doing it, or do it together. What we believe is, really don't catch a fish for somebody and feed him. What we believe is, let me catch a fish for you, so we'll solve the problem together, but then I will teach you how to fish so you can feed yourself for life. So we don't really just do an engineering project. If you have the tools, we'll help you how to do it. But if it's a rush project and you need in 2 weeks a very sophisticated multi-physics design, I'll be delighted to review the problem. And some problems are not doable, okay? So you don't need, again, don't believe the software vendors that we can do everything. You need to, to be realistic, and we'll be glad to evaluate it.
Wonderful. We have another question from Ahmad. Do boundary conditions from CSL move to the advanced simulation tools?
Not to my knowledge, but the boundary conditions are so simple. You have inlet velocity and outlet pressure,
Wonderful. Thank you very much.
So I think that's most of the questions that have come in from the chat. If anybody else has questions on the phone, and also my friend from PTC, Nelson, is on the phone. Nelson, if you had anything you wanted to add, raise your hand and we will pass over a speaker to you. And I think, Nelson, you're live.
Hey, yeah, thanks. Just a quick mention, Creo Simulation Live introduced the fluids analysis like was shown today with Creo 7. So if you're planning to use it today, you'll want to upgrade to Creo 7, which has been out for a month or two. Just wanted to add that little side note there.
You can find a recording of the recent Creo 7 webinar that we performed on our website.
Yep. Okay, closing thoughts, Andreas?
Yes, that this is very, very exciting time. You need to, what we found out the biggest problem implementing this stuff is the IT department. Because you ask them and they say, oh, we're still in Creo 4 because the transition is hard or whatever. Please move on. Like the thing you see on the screen, I don't know if you still see my screen, this lattice structure is one feature. It's for a long time in Creo, but they're improving. And then you can find its temperature, and then you can design it. You can make the spacing more or less. So I urge you, I think you will be excited to move on to adopt the latest releases of the software. That's the number one. The number two, the learning curve is very, very simple. It's very simple. You can, in half a day, I can show you everything you need to know in Creo Simulation Live to do all 4 types of analysis, and and then you will be able to do it. This is a design enabler tool. Is bringing, if I summarize my points I had earlier here, to see if we make this is simulation driven design. Finally, the design is being enabled. I did projects with big automotive and aerospace companies, and they give you a problem, they give a problem to the analysis team work on it for a couple of weeks, and then they come back with a big smile in their face and say, oh guys, if you change that fillet to this, and if you change that thickness to that, and if you change that height to that, then it will be better. And then the designer team looks at them with a puzzle in their face, and they're thinking, oh my God, these guys are so irrelevant now. We have moved the design for 2 weeks to totally different state because of manufacturing or weight limitations or interference and stuff. So now they're irrelevant. What do we tell them? So finally simulation becomes relevant because you can put it within the design environment. Okay, you utilize it in the simulation process. You get very quick answers to what if questions. If I change in the heat exchanger the diameter, will it influence my temperature? You don't need to worry about fluid domains or inflation layers and etc. You can do, as I show you, optimization or design exploration on the fly. You can do breakthroughs in innovation. You can innovate. Why? Because you have an idea and you can test it very quickly. I would love to show you, heat exchangers with gyroids, which they're amazing geometries we couldn't even dream before. So innovation, believe it or not, is a necessity. It's not a luxury. So these tools enable you to do that innovation. So reach out, learn them on your own, or contact Chris or Hannah to set up a training for you. We can do it virtually if you need to right now. And enjoy the stuff. I mean, PTC put a lot of effort to make these things. They're getting better and better every day, and they help you do higher performance products. And why do you care about higher performance projects? You can say, oh, we're the leaders in elevators or whatever. You do. You need to keep leapfrogging yourself on product performance so you can keep the leadership position or leapfrog your competition. Anyway, I think I should stop.
Thank you, Andreas. Appreciate that. And then there was one last question, and probably a follow-up from Nelson. Danny Chavez with NOV, I assume that's National Oil Barco. Question was regarding if both products shown require Creo 7, and I believe the answer is no. The first one, which was the Creo Flow extension, is an extension and is not require 7. But the Creo Simulation Live with flow analysis does require Creo 7.
Yeah, only the flow analysis is in 7, but the structural, thermal, and modal in all of them, you know, they went backwards.
Yep, I can contact Danny, and there's at least 24 people at NOV using CSL in our group today at multiple sites, so I'll reach out.
Okay, very good. Okay, then at this point, Hannah, anything else you want to close?
No, it's 11:01 at this point. So I appreciate everyone joining us today. And a recording will be available in the next couple of days. I will send it out to all the attendees, and we look forward to speaking with you in the future.